Welcome back to Basic Electronics. In this lecture, we will continue with Schmitt triggers. We will look at a Schmitt trigger circuit which allows the threshold voltages VTH and VTL to be shifted using a reference voltage. We will then start with a new topic, namely sinusoidal oscillators. First, we will discuss the principle behind these circuits and then look at some specific examples. Okay, let us start. Let us look at this modified Schmitt trigger circuit with the VO versus VI relationship shown here. Essentially, it's an inverting Schmitt trigger, but here the VTL and VTH are not symmetrically placed around VI equal to 0. They have been shifted along the VI axis, and this shift depends on this reference voltage, as we will find out. This reference voltage can be adjusted using a pot, which we have not shown in the figure. And our task is first of all to understand how this circuit works, and then we want to design it to obtain V0 equal to 2.5 volts, where V0 is this voltage here at the center of this interval between VTL and VTH. So that is one design specification given to us. The other specification is delta VT, which is the difference between VTH and VTL. This difference should be equal to 0.4 volts. And once we design the circuit, then we will simulate it and make sure that it works as we designed it. And you can also go to your electronics lab, set up the circuit and verify its operation. Let us now try to understand how this circuit works. Let us say we are somewhere here on the VO versus VI curve. That means our VO is plus Vm and VI is, let's say, 0 volts. And now we are increasing VI, and at VI equal to VTH, the output is going to flip from plus Vm to minus Vm. So the key point is this V plus. When our VI, which is equal to V minus, crosses V plus, that is when this output is going to change from Vm to minus Vm. So let us find what that V plus is in that situation. So we have VO equal to plus Vm, which is 14 volts. VR is a constant DC voltage, for example 2 volts, and this current is 0 because that's the input current for the op amp. And in this situation we can use superposition to find V plus. We have two voltage sources, VR and Vm. We can take them one at a time, find V plus in each case, and then add the two V plus values. Let us consider VR first with this voltage equal to 0. That means this node is at ground potential, and then R2 and R3 are in parallel. And in that case, V plus can be obtained simply using voltage division, and V plus would be VR times this resistance, which is R2 parallel R3, divided by R1 plus R2 parallel R3. That is the first term here. Next, we consider this voltage, that is Vm, and take VR as 0. Now what happens is R1 and R2 come in parallel, and V plus, once again using voltage division, is given by Vm, the potential here, times R1 parallel R2 divided by R3 plus R1 parallel R2, and that is the second term over here with the plus sign. So that is V plus when VO is equal to plus Vm, and that essentially gives us VTH. Similarly, when we are here, VO is minus Vm, and now V plus is the same expression with a minus sign here, and that gives us VTL. And now let us look at the specs that we have been given. Delta Vt, which is the difference between VTH and VTL, has been specified as 0.4 volts, and when we subtract VTL from VTH, this term drops out and we get 2 times Vm times this voltage division factor. So that should be equal to 0.4 volts, and that is our first condition. The second specification is that V0 should be equal to 2.5 volts. What is V0? It is nothing but VTL plus VTH divided by 2, and when we add VTL and VTH, this second term drops out, because in VTL we have a minus sign here, and in VTH we have a plus sign here. So what we get then is VR times R2 parallel R3 divided by R2 parallel R3 plus R1 equal to 2.5 volts. So let us now use these two conditions to design our circuit. For delta Vt to be 0.4 volts, we want this quantity to be 0.4. Vm is already known, that is the same as Vsat for the op amp, given to be 14 volts. So we should now select suitable resistance values so that this fraction multiplied by 2 Vsat gives us 0.4. Let us make a choice here. Let R1 and R2 be equal, and let us call that R, and let that be 5K. In that case, this quantity can be replaced with 2 times Vsat. R1 parallel R2 becomes R parallel R, that is R by 2. So R by 2 in the numerator, R by 2 plus R3 in the denominator, and R is already known. We have selected that to be 5K. So this equation can now be solved for R3, and R3 turns out to be 172.5 K. Our other constraint is V0 equal to 2.5 volts. That implies that VR times R2 parallel R3 divided by R2 parallel R3 plus R1 should be 2.5 volts. Now the resistance values are already known. R3 is 172.5 K, R1, R2 are equal 5 K each. So this number can be calculated, and that gives us VR equal to 5.07 volts. So this reference voltage should be 5.07 volts. In practice, of course, it's going to be adjusted using a pot. Alright, now we're going to simulate this circuit, and in fact the circuit file is available to you. You can also run this simulation if you like, and let's now confirm with the simulation results that our design is correct. Here is the circuit schematic. We have R1 equal to R2 equal to 5K, R3 is 172.5 K, and VR, the reference voltage, is 5.07 volts. As input, we have applied a sinusoidal voltage here, and let us now look at the results. So this is the input voltage, and that is the output voltage. So the output voltage is plus 14 volts here, that is plus Vsat. Then it changes to minus 14, that is minus Vsat, and then back to plus Vsat. This is the VO versus VI plot. This is our VTL, that is 2.3 volts. This is our VTH, 2.7 volts. And we now need to check two things. One, delta VT, that is the difference between VTH and VTL, should be 0.4 volts. This is 2.7, this is 2.3, so the difference is indeed 0.4 volts. Second, the center of this interval, which we have called as V0, should be 2.5 volts, and that is also observed over here. So that shows that our design is correct. We will now look at sinusoidal oscillators which produce sinusoidal output voltages, and we begin with an amplifier with feedback as shown in this picture. Here is an amplifier. Its input is xi prime, its gain is A, so the output is A times xi prime. And let us remember that all of these quantities xi prime, xi, xf, xo are phasors. Alright, now this is our output, so xo is equal to A times xi prime, and part of this xo, namely beta times xo, is fed back here as xf. So xf is beta times xo. That gets added to the amplifier input xi, and that produces xi prime. So xi prime is xi plus xf, because we have this plus signs here. So that completes the picture, and let us now look at how xo and xi are related. Let us start with xo, which is A times xi prime. What is xi prime? It is xi plus xf, so we put that here. And xf is beta times xo, so we substitute that over here, and finally end up with A times xi plus A beta times xo. Now this term, which contains xo, can be taken to this other side, and then that gives us a relationship between xo and xi. And the ratio of xo and xi is called AF, that is the amplifier gain with feedback, and that is given by A divided by 1 minus A beta. It simply follows from this equation here. Since A and beta will generally vary with omega, we rewrite AF as a function of j omega to indicate that it is a function of omega, equal to A of j omega, the amplifier gain, divided by 1 minus A of j omega times beta of j omega. This network is frequency sensitive, so it definitely has a frequency dependence, and that is denoted by this beta as a function of j omega. Now what happens if A times beta becomes 1? The denominator will become equal to 0, and then AF will tend to infinity. And then what happens? Then we get a finite xo, which is equal to AF times xi, even if xi is very, very small or 0 in the limiting case. So we are getting an output even without supplying an input. In other words, we can remove xi, so this part can be removed altogether, and still get a non-zero xo. And that is the basic principle behind sinusoidal oscillators. What is the condition for oscillation? We should remember that is A times beta at the frequency of oscillation should be equal to 1. Okay, so let us make some important points. The condition A times beta equal to 1 for the circuit to oscillate spontaneously, that is without any input, is known as the Barkhausen criterion. For the circuit to oscillate at a certain frequency, omega equal to omega 0, the beta network, this network here, is designed such that the Barkhausen criterion is satisfied only for that specific frequency omega 0. That is, all other components except omega 0 will get attenuated to 0, and that is how we get purely a sinusoid at the output. So the output XO will therefore have a frequency omega 0, or if you want it in hertz, then it's omega 0 by 2 pi. But we haven't really said anything about the amplitude. So that is the next question we want to address. Here is our feedback amplifier, and as we have seen, this circuit will oscillate. That is, we can even remove this Xi and still get a sinusoidal output if we satisfy the Bark-Huysen criterion, which is A of j omega, this A, times beta of j omega equal to 1. So the product of these two should be equal to 1, and that will happen only at one specific frequency. Let us call that omega 0, and that is what we will get at the output. So XO will be a sinusoid of frequency omega 0. But we have not said anything about the amplitude, and let us discuss that now. Here is a block diagram which illustrates how we can limit the amplitude of the oscillations. And notice that we are not showing Xi in this block diagram. We assume that the Bark-Huysen criterion has been met, the circuit is oscillating freely, and therefore an input voltage is not required. So that is 0, and Xf, which is equal to beta XO, is connected directly to the amplifier, like that. Alright. A gain limiting mechanism is required to limit the amplitude of the oscillations. Here is a schematic diagram showing gain limiting. What do we have here? We have VO versus VI relationship indicated in this graph. Let's say this is our VI and that is our VO. In the central part, we have a slope of 1, and here the slope is smaller. So what it means is, if the amplitude becomes large, then it tries to reduce the output voltage. In practice, these are not implemented separately sometimes, and we might see that these two are combined. But as a schematic representation, this is adequate for us. Now there is some natural gain limiting mechanism in amplifiers. Amplifier clipping can provide a gain limiter mechanism. For example, in an op-amp, the output voltage is limited to plus minus Vsat, as we have already seen, and this serves to limit the gain as the magnitude of the output voltage increases. But what is normally done is a separate gain limiting network is used. For a more controlled output with low distortion, diode resistor networks are used for gain limiting. And let us take some examples of such networks to understand what is happening. Okay, here is a gain limiting network example, and exactly how we are going to use it we will not comment on right now. We will look at some oscillator circuits later and see how that fits in. Right now our interest is what this I looks like as a function of V. When these diodes are not conducting, the only resistance in the picture is this R1, and therefore I versus V will have a slope of 1 over R1. As we increase V, at some point D1 will turn on, and now we have two current paths, that, and that will cause a change in the slope of the I versus V relationship. Similarly, if we make V negative and keep increasing it in the negative direction, at some point D2 will turn on, and then we will have this current as well as that current, and that again will change the slope of the I versus V relationship. So let us now look at what the IV looks like. Here is the I versus V relationship, the top plot. Now if we look at this central region, that is where the diodes are not conducting, and the only resistance then is R1, and that slope is 1 over R1. Remember that we are plotting I versus V, so the slope will have units of conductance. Now as we increase V in the positive direction, around here D1 turns on, and now what happens is R1 and R2 come in parallel. So the slope now becomes 1 over R1 parallel R2, and since R1 parallel R2 is smaller than R1, this slope is larger than this one. So the slope has increased. And the same thing happens also in the negative direction. As we increase V in the negative direction, at some point D2 turns on, and again the slope increases over here compared to this slope. In this bottom plot, we have plotted dV di, that is the derivative of this voltage with respect to this current, in kilo ohms as a function of the applied voltage V, this V here. Now in the central region, when the diodes are not conducting, this branch is not there, and the only resistance then is this R1, and therefore what we expect for dV di is simply R1, which is 2K, and that is what we see over here, that is 2K. Now as we increase V in the positive direction, at some point D1 starts conducting, and this is a real diode. It's not a diode which starts conducting abruptly at 0.7 volts, and so therefore the variations are smooth as shown here. When this diode starts conducting, the net incremental resistance is now reduced because we have now two parallel current paths, and then the resistance goes down. Eventually what happens is the diode is conducting so heavily that its own resistance is very small, 0, and then all we see is R1 and R2 in parallel, and that is what we can see over here. What is R1 parallel R2? It is 1K, and that's exactly what we are seeing over here. And the same thing happens also in the negative direction. Somewhere here D2 starts conducting, and the resistance, the incremental resistance dV di falls and eventually becomes equal to 1K. So let us remember this picture. When we talk about oscillator circuits, this picture will be relevant in limiting the gain. Second example, we have two diodes here, T and D prime, and we want to look at how this current I varies as a function of this voltage. This VCC is a power supply equal to 15 volts, minus VEE is minus 15 volts, and the resistance values are indicated here in the figure. Alright, now the way this circuit works is for small voltages, neither D is on nor D prime is on, and the only resistance in the circuit is this R here, and that is our conduction path. And when D prime and D are both off, this node is at 15 divided by 75 times VCC with respect to this node here, simply by voltage division. Let's say we are taking this as a reference or ground. With respect to that ground, this node voltage is 3 volts when D prime is not conducting. Now if we keep increasing V, at some point this voltage will become larger than 3 volts, and it will become 3 plus V on of this diode, and now the diode will start conducting. And now some additional resistors are coming in parallel with R, and the net resistance will then go down. So that is roughly how this circuit works. And similarly, when we increase V in the negative direction, at some point this diode D turns on, and once again the slope of the I versus V relationship changes. Here is the current versus voltage plot, the top one. In this central region, D and D prime are both off, and the only resistance in the circuit is then this 20K, and therefore this slope is 1 over 20K. At this point, D prime turns on, and that is between 3 volts and 4 volts as we expect. Now there is this additional current path, and therefore the net resistance goes down, and therefore the slope, which goes as 1 over R, increases. The same thing happens in the reverse direction. Somewhere here D turns on and the slope increases. And in fact, when we were looking at diode circuits, we have seen circuits like this, and you should be able to actually find out what this I versus V should look like theoretically. And in that calculation, we can treat this D prime and D to be ideal diodes with a turn on voltage of, let's say, 0.6 volts or 0.7 volts, and you should be able to calculate all of these slopes. Alright, now dV/dI in kilo ohms is shown in this bottom plot as a function of the applied voltage V. In this central region, since R is the only resistance in the picture, we get dV/dI equal to R, which is 20K. That is what we see here. As D prime starts conducting, the resistance starts going down, and when D prime conducts sufficiently strongly, finally what happens is this 20K, 15K and 60K, they all come in parallel, and that gives us this resistance here, and that turns out to be something like 7.6K or so. And the same thing happens also in the negative direction. Here D turns on, and then finally 20K, 15K and 60K come in parallel, and that gives us this resistance value here. To conclude, we looked at a Schmitt trigger circuit in which the threshold voltages can be adjusted using a reference voltage. We then started our discussion on sinusoidal oscillators and described the basic principle of operation for these circuits. In the next class, we will consider specific examples of sinusoidal oscillators. So see you next time.